Happy December 16th. I want to talk today about a couple of my favourite particles. These are quite low energy particles compared to what we're used to these days, and one of them is the X3872. I've talked about this before on my blog, and it's a particle that sort of came out of nowhere. Nobody really expected to see it. Now the Barber and Bell experiments, and there were a few other experiments at Fermilab that had seen it before Barber and Bell had seen it, but Barber and Bell saw it unambiguously when they were looking at some other decays. Now, the X3872 is called the X because when we first discovered it, we didn't really know what it was. We knew it liked to decay to what's known as the J-psi meson and then 2 pions. Now, the J-psi meson is really nice because that likes to decay to things like muons and electrons, and it's got a very narrow shape. So you have this spectrum of the invariant mass of 2 muons, and it falls down like this, and you get a huge peak, and then it falls off again. And this huge peak is the J-psi, and that means that you can get a sample in data which is very pure in J-psi. All you have to do is you have this distribution, you cut away events, and you have just this peak, and that's 95% J-psi. And then what you can do is see what is decaying into this J-psi. And when you add 2 pions, you end up with a small bump in your distribution. So you'll have the invariant mass of 2 muons and 2 pions. You then place a selection on the mass of the 2 muons to get your J-psi peak, and you end up with an invariant mass of the 4 objects that looks like this. It falls off, and you get a bump. It falls off again. And this bump is the X3872. Now, we try to look for it decaying to other things. Now, it decays to the J-psi, and that means it probably has charm and anti-charm in there, and so we'd expect it to also decay to D mesons and D bar mesons. But we generally don't see that, even though it's got enough energy and the right quantum numbers to do that. So people started looking at this in more detail, and a lot about the X3872 is unknown, but the current best theory suggests that it's actually a molecule of 2 D mesons. So there's 2 D mesons, they're close to each other, and they're in a sort of bound state. And then the charm-anti-charm pair meet, annihilate to give us the J-psi, and at the same time they produce 2 pions. It can decay to other things as well, but we really don't know enough about it to be able to say what else it decays to. Now, in addition to the X3872, I also wanted to talk about another meson called the DSJ. And one of the reasons I like this, apart from the fact the name is DSJ, which is really cool, is that at first it wasn't discovered. People discovered the DS meson, and that's actually the meson that I studied in my PhD thesis, so I know quite a lot about that meson. And they looked at spectroscopy, and they wanted to find all the different states that is the best meson. And one of the ones they missed out was the DSJ. The reason for this is because it has quite a long lifetime, because it's a charm quark and a strange antiquark spinning around each other. We've got large angular momentum, and that makes it have a lower lifetime than expected. And so spectroscopy was performed, they had all these different states, and then somebody went back and said, wait a minute, I think there's something we're missing here, and they found the DSJ. Anyway, I think they're really cool particles. The X3872 is mysterious. It's telling us something about how these mesons can actually form bound states, and the DSJ is a variant of the meson I studied in my thesis. And it's one that when you sort of go back and look for it expecting to see it, you see it, and until then you don't see it. Okay, I'll see you tomorrow.